Hello, in this podcast we're going to learn about two-dimensional motion. The different aspects of that are position, velocity, and acceleration vectors, analysis with unit vectors, projectile motion, and then also talking about relative velocity and acceleration. Let's move on to talk about our position, velocity, and acceleration vectors. Let's talk about some terminology. R is the two-dimensional position. It's made up of x and y. Delta r is the two-dimensional displacement. It's made up of delta x and delta y. Please note that delta r, the two-dimensional displacement, is not equal to the distance or the path length. Theta is the angular direction of the vector. The absolute value of delta r is the magnitude of the displacement vector, and absolute value of v is the magnitude of the two-dimensional velocity. Let's take a look at our position, velocity, and acceleration vectors. And here we have an object where it's plotted here. Its path is plotted on an XY graph. So initially the object is moving vertically upward and horizontally to the right, and then it starts to move downward while it still continues to move horizontally to the right. We've got 2 points, point P, which we'll consider the initial time, or occurring at the initial time. We have position Q, which occurs at the final time, T sub f. If we look first at the position vector, it's defined as the unit vector I times the scalar magnitude x plus the unit vector j multiplied by the scalar quantity y. So this is just the two-dimensional position vector written in unit vector notation. Then we have the term delta r. This is also a vector. It's the change in two-dimensional position, and it's the final position minus the initial position. And you can see here we've drawn that vector delta r, and visually we can see that the vector arrow starts at the position P and ends at the position Q. This visually represents the same vector that's represented mathematically here. Moving on to velocity, first talking about average velocity. Average velocity is defined as the change in displacement divided by the elapsed time. So notice in this equation, the only vector quantity we have is in the numerator, the change in position, because change in time is a scalar quantity. Therefore, the velocity, or the average velocity vector, is going to be in the same direction as the change in position or displacement vector. But its magnitude is going to be different. It's going to be 1 divided by delta t times the delta r vector. So if delta t is larger than 1, then the average velocity vector will have a magnitude smaller than the displacement vector. On the other hand, if delta t is smaller than 1, then the average velocity vector is going to have a magnitude larger than delta r. Let's talk about instantaneous velocity, because of course that's different than average velocity. Notice here I have arrows above the vector quantities. This is typically how we represent vectors as opposed to just the magnitude of vectors. However, I'm very sloppy about that, and I usually don't put the arrows above, which is why in the previous slide I said that for magnitudes I'll use the absolute value sign, and then when you just see the symbol, that's the vector. However, technically vector quantities should have an arrow above their symbol. Okay, so back to the instantaneous velocity. It's defined as the limit of the displacement vector divided by the elapsed time as elapsed time goes to 0. And of course we know that as the derivative of r with respect to the derivative of time. Now, based on our previous definition of the average velocity vector, it would be pointing in the same direction as the displacement vector, which would be from P to Q. But if you can imagine, as the time between P and Q gets shorter and shorter, this Q position is going to get closer and closer to the P position, and when you do the delta r vector, you can see that it's going to change direction, and as delta t approaches 0, the instantaneous velocity vector points in the same direction as the tangent line at point P for the instant velocity at position P, and the instantaneous velocity at point Q points in the direction of the tangent line at point Q. So let's look at average acceleration. Average acceleration is the change in velocity divided by the elapsed time. So if we look at our final velocity and initial velocity vectors, I just transferred these from the previous drawing, we're subtracting them. So that means we have the final velocity arrow, but then we subtract from it the initial velocity arrow. So that means we have to take the initial velocity arrow and turn it in the other direction. That's how we do our vector subtraction visually. And that leaves us with the delta v vector, the change in velocity vector. Notice that just like the change in position vector was in the same direction as the average velocity vector, the same thing holds true here with the average acceleration. The average acceleration vector points in the same direction as the change in velocity vector. So the instantaneous acceleration is defined as the limit of the change in velocity vector divided by the elapsed time as the elapsed time goes to 0. And of course, this leads us to the calculus definition that the instantaneous acceleration vector is the derivative of the velocity vector with respect to time. So delta v and hence acceleration are caused by changes in speed, which is the magnitude of the velocity vector, and direction, or both. Let's look at how we can use unit vectors to help in our two-dimensional motion analysis. First, we'll start with position vector, and of course that's made up in unit notation of magnitude x times the I unit vector plus magnitude y times the j unit vector. To express the velocity vector in unit notation, we have to take the derivative of r with respect to time, and that gives us dx dt times the unit vector I plus dy dt times the unit vector j. And then to get acceleration in unit vector notation, we need to take the derivative of velocity with respect to time. So we need to take this quantity and differentiate it again with respect to time, and that gives us the second derivative of x with respect to time times the I unit vector plus the second derivative of y with respect to time times the j unit vector. Now that we have those definitions for our unit vector quantities, we can look at what this means in terms of constant acceleration. And for this, we're going to refer back to some of the kinematic equations we developed in our previous course for uniform acceleration. What we often refer to as kinematic equation 1 is the velocity is equal to v sub naught plus a times t, and what we often refer to as equation 2 is the position is equal to x sub naught plus v sub naught times t plus 1/2 a times t squared. So if a is a constant, then it stands to reason that a sub x and a sub y must also be constant. Keep in mind that a sub x is the magnitude scalar that's multiplied by the I unit vector, and a sub y is the magnitude scalar that's multiplied by the j unit vector. We can use these two equations to come up with expressions for displacement and velocity in terms of acceleration. First, let's look at velocity. So our velocity unit vector notation is going to be v sub x times I plus v sub y times j. Notice if we take equation 1 here and we substitute this for v sub x and v sub y, we have the unit vector notation for the instantaneous velocity vector as v sub naught x plus a sub x times t times the unit vector I plus v sub naught y plus a sub y times t, that times the j unit vector. And we can use equation 2 up here and substitute in for x and y in our position unit vector notation, and that gives us x sub naught plus v sub naught xt plus 1/2 a sub x t squared, that quantity, times the unit vector I, plus y sub naught plus v sub naught yt plus 1/2 a sub y t squared, that quantity in parentheses, and notice I'm missing the parentheses here, but this quantity in parentheses times the unit vector j. So now we have expressions for our different unit vectors in terms of a. Now note, they're only true or only valid when we have constant acceleration. Let's look at an example and see how we use this to do problem solving. So here we have a particle that starts at the origin and it moves with a uniform acceleration of 2.0 I plus 4.0 j meters per second squared. Again, this is giving you the magnitude of the horizontal acceleration, and this is giving you the magnitude of the vertical acceleration. And its v sub naught, or initial velocity, is 40 times I plus 20 times j meters per second. So this means that the initial velocity in the horizontal dimension is 40 meters per second, and in the vertical dimension 20 meters per second. So we want to find its total displacement and velocity vectors. Total can also be known as the resultant vector, and we want to find it at time equals 2 seconds. Well, let's look at the position or displacement problem first. So we want to look at our position at the end of 2 seconds. So we're going to go ahead and put in our equation from the previous page. This is x sub naught. This is this is x sub naught. This is v sub naught x times time, 2 seconds, and this is 1/2 times a sub x times time squared. Over here, we're also putting in y sub naught, and again, these x sub naughts and y sub naughts are 0 because the particle started at the origin. We get our v sub naught right here, 20 meters per second times the time we're evaluating it at, which is 2 seconds, plus here's our acceleration term, 1/2 times the vertical acceleration, which we get right here, times time squared, times the unit vector j. And the m here is just to indicate that the units are in meters. So if we go ahead and do the math here, this expression turns out to be 84, and this expression here in brackets turns out to be 48. So our position vector after 2 seconds is 84 I plus 48 j meters. To find displacement, we need to take our our final position, which is at time 2, that's what we just calculated here, minus our position at time 0. Well, it started at the origin, so our initial position was 0 I plus 0 j, and our position at 2 seconds was 84 I plus 48 j. So to get our displacement vector, it'll be the x position at 2 seconds minus the initial x position, 84 minus 0, and it'll be 48 meters, which is the vertical position at 2 seconds, minus 0 meters, which is the vertical position at time equals 0. And of course, it asked us to come up with the vector. So this is one way of expressing the vector notation. But if we wanted to find, and that would be okay to leave it in this unit notation. That is specifying the vector. If we wanted to express it in terms of the magnitude, we'd use this modified version of the Pythagorean theorem, and we'd find out that the magnitude of the displacement was 96.7 meters. We are just taking the magnitude of in the horizontal direction, squaring it, plus the magnitude of displacement in the vertical dimension, squaring it, taking that sum and the square root of that sum. Then to find the directional angle theta, which is the angle measured counterclockwise from the positive x-axis, we would take the inverse tangent of the y magnitude, or the vertical magnitude, divided by the x magnitude. And that would give us 29.7 degrees. Let's move on and take a look at the velocity vector. Here we use our formula from the previous slide, and the v sub x velocity magnitude is just v sub naught x plus 2 times the acceleration. So the v sub naught x was gotten right up here from our v sub naught unit vector, and the 2, which is the acceleration, was gotten here from our unit vector for acceleration, and of course the 2 here is the time that was defined in the problem. Then for the vertical component, the magnitude of the vertical unit vector j, we get the initial velocity 20 from our initial velocity vector, and we get the vertical acceleration of 4 from our acceleration vector, and once again the 2 is defined in the problem as 2 seconds. So when we go ahead and calculate this, our velocity vector in unit notation is 44I plus 28J meters per second. That's perfectly acceptable way to express the velocity. But if you were asked to find the magnitude of the velocity and the direction of the velocity, you again would use the modified version of the Pythagorean theorem with the x component velocities and y component velocities, and you would find that your total or resultant velocity magnitude was 52.2 meters per second, and the directional angle theta would be the inverse tangent of 28 meters per second divided by 44 meters per second, and that would give you 32.5 degrees. Notice that the direction of the instantaneous velocity vector is not the same as the direction of the displacement vector. And at first we may think this is at odds, but it really isn't. If we remember that the instantaneous velocity vector is in the same direction as the displacement vector as the limit of delta t goes to 0. And here we did not calculate the displacement vector for the limit as delta t goes to 0. We calculated the displacement vector for 2 seconds. So the shorter and shorter this time period gets, the closer it gets to 0, the closer this directional angle for displacement is going to get to the instantaneous velocity direction angle. But until the velocity, until delta t reaches 0, they'll never be exactly the same. Next, let us take our two-dimensional vector equations and apply them to the special case of two-dimensional motion known as projectile motion. In our analysis, we're going to ignore air resistance, and that leads us to the following assumptions. In the horizontal dimension, the acceleration is 0, and in the vertical dimension, acceleration is free fall, which near the surface of the Earth is negative 9.8 meters per second squared. So let's take a look at our position function in unit vector notation. And for this, we're going to go ahead and take kinematic equation 2 and substitute it in place of the horizontal magnitude and the vertical magnitude. Notice here in the horizontal component we're missing the 1/2 a t squared term because acceleration is 0, so that all goes to 0. So the horizontal component of the position is x sub naught plus v sub naught x times t, and the vertical component or magnitude of the position is y sub naught plus v sub naught y times t minus 4.9 t squared. Let's take a look at the particle's velocity function, and we are now going to make a substitution for the horizontal and vertical magnitudes using kinematic equation 1. So of course, since acceleration is 0, the magnitude of the horizontal velocity is always going to be v sub naught x, and then the vertical velocity will change according to the equation v sub naught y minus 9.8 t. So this is how we would express velocity in terms of unit notation and calculate it based on a given time. Now, if you were asked to find the magnitude of velocity, you would simply apply the Pythagorean theorem to our unit vector notation, and to find a directional angle theta, you would apply our inverse tangent equation. And you can use the Pythagorean theorem to find the magnitude of the displacement vector and also our inverse tangent formula or equation to find the directional angle of the displacement vector. I just didn't show them here. Okay, let's move on to some special cases of projectile motion. First, let's think about maximum height. Well, we have to remember that maximum height or peak height occurs when the y component of velocity is 0, and then the height is going to be defined as y minus y sub naught, where y sub naught is the vertical position at time 0, and our third kinematic equation, which tells us that the y component of velocity at time t squared minus the initial y component of velocity squared is equal to 2 times the acceleration caused by gravity times the vertical displacement, or in this case, height. So if we go ahead and rearrange this last expression to find height, we're left with the height is equal to v sub naught y squared divided by 2g. We can replace v sub naught y, the vertical component of initial velocity, with the total component of initial velocity, because we know that v sub naught y is equal to the initial velocity times sine theta. And we make that substitution and we're left with the maximum height is equal to negative v sub naught squared times sine squared theta. Notice this is not squaring the theta, this is taking the quantity sine theta sub naught and squaring it, divided by 2g. Now, in some textbooks, they'll express g as positive 9.8 instead of negative 9.8, and when they do that, this negative sign goes away. So if you see this formula, and it may be in your reference sheet this way, where the negative sign is missing, that's because they're treating the acceleration due to gravity as a positive number and not a negative number. And then, of course, theta sub naught is just the initial launch angle. Similarly, we can come up with an equation for the horizontal range. So we know the horizontal range happens at time equal to twice the time of the maximum height. And again, assuming no air resistance and assuming that the launch height and the landing height are the same, it takes as long for the object to come down from its peak height as it took to arrive at its peak height. We can use kinematic equation 1 and come up with an expression for time at the maximum height, and that is equal to the negative of the initial vertical component of velocity divided by the acceleration due to gravity. And we can substitute our trigonometric expression for v sub naught y, and the maximum height, or the time to the maximum height, is equal to negative the initial velocity times the sine of the initial launch angle divided by the acceleration due to gravity. Finally, we know that the range is going to be equal to x, the horizontal position at time t, minus the horizontal position at time 0. We can use these governing equations to come up with an equation for the horizontal range. So the range is just going to be equal to the horizontal speed, which remains constant at v sub naught x, times how long it's in the air, and that is twice the amount of time it takes to reach the peak height. Now, we can take v sub naught x and we can write it in terms of the initial velocity v sub naught times cosine theta sub naught. And we can take t max height and write it with this expression, negative v sub naught sine theta sub naught divided by g. And we can rearrange, and that leaves us with negative 2 v sub naught squared sine theta sub naught times cosine theta sub naught divided by g. Now we can use a trigonometric identity and simplify this to the range is equal to negative v sub naught squared sine 2 theta sub naught divided by g, the acceleration due to gravity. Now the same caveat applies here as I mentioned up here. In textbooks you'll often see this formula without the negative sign, and when they do that they are treating g, the acceleration due to gravity, as a positive number, 9.8 meters per second squared, close to the surface of the Earth. This wraps up our discussion on two-dimensional projectile motion. Now let's study another type of two-dimensional motion, which is relative velocity and acceleration. When we measure velocity and acceleration, it's always relative to a particular reference frame. So for instance, when you're driving your car, and a speedometer shows 30 miles per hour, it's measuring the car's velocity relative to the ground. On the other hand, if somebody, say a police officer, was behind you and you were traveling 30 miles per hour and the police officer was traveling 20 miles per hour and they aimed their radar gun at you, they would observe your speed not as 30 miles per hour, but something slower than that. So in this section we're going to learn how to calculate these relative velocities and accelerations. We're going to calculate these quantities from two reference frames, the stationary observer, located here on this sketch, and their reference frame is S, and the moving observer, whose reference frame is S prime, located here. Now, we're going to do this process for an observer moving to the right, but what I'm doing here or showing you here will work whether the observer is moving to the left or moving up or moving down. So let's talk about a few more definitions. The velocity, well, the stationary observer is stationary, so velocity is 0, and the moving observer is moving with a velocity of u relative to the stationary observer. The stationary observer's position is 0, and the moving observer's position we'll call 0 prime. The particle's position vector from the stationary reference frame is vector r, and the particle's position vector from the observing mover's reference frame is r prime. Now there's one other important vector quantity, and that's the distance between, or the displacement between, the stationary and moving observer, and that vector has a magnitude of u times t. In other words, that's going to be changing because the longer time goes on, the further away the moving observer is from the stationary observer. Now let's look at the relationship between the particle's position vectors from these two reference frames. And for this, let's take a look at, or remember back to, our visual method of adding vectors. If we look at the displacement vector between the stationary reference frame and the moving reference frame, that is u times t. And then the particle's position from the moving observer's reference frame is r prime. Well, notice r prime vector starts at the head of the ut vector, and then notice that this reference, or the particle position vector for the stationary observer, it starts at the tail of the ut vector and it ends at the head of the r prime vector. So this vector r is simply the addition of these two vectors ut and r prime, and that leaves us with an important relationship that the particle's position vector from the stationary frame is equal to the position vector from the moving frame plus u times t. Now we can go ahead and rearrange this equation to state r prime, and r prime is equal to r minus ut. So let's move on and define the relative velocity and acceleration vectors. So velocity is defined as the change in position with respect to time. So the velocity from the stationary observer's reference frame is dr dt. Now in the previous slide we had an expression for r, it's r prime plus ut. So we can take the derivative of this quantity in parentheses with respect to time, and that leaves us with dr prime dt plus u. Now dr prime dt is the definition of the instantaneous velocity from the moving reference frame, which we call v prime. So now we know that the velocity from the stationary reference frame is equal to the particle's velocity relative to the moving frame of reference plus the velocity of the moving frame from the point of view of the stationary observer. Now that tells us we can do the same thing with an expression for v sub prime. So v sub prime, which is the particle's velocity from the moving reference frame, is equal to dr prime dt. We know that we can substitute r minus ut in place of the r prime, and when we differentiate this expression in parentheses, we're left with dr dt minus u. Now dr dt is the definition of the particle's velocity from the stationary observer's reference frame. So the velocity of the particle in the moving reference frame is equal to the particle's velocity in the stationary reference frame minus the velocity difference between the moving frame and the stationary frame. Now let's take a look at acceleration. The acceleration of the particle from the stationary reference frame is dv dt, and of course we have another expression for v, and that's v prime, the particle's velocity from the moving reference frame, plus u, which is the velocity of the moving frame relative to the stationary frame. So when we differentiate this, we get dv prime dt. The u goes away because that's a constant. And similarly, we can take a prime, and that's equal to dv prime dt. And we can substitute our expression for dv prime, which is v minus u, and that winds up being dv dt. So here, the acceleration from the stationary reference point of view is equal to the acceleration from the moving point of view, and the same thing holds true when we look at it this way. So we can conclude that the acceleration of the particle is the same whether you're viewing it from the stationary reference frame or the moving reference frame. Let's take a look at an example. We have a boat traveling 9 meters per second east relative to an observer on the shore. The ocean current is moving 3 meters per second north. A seagull is floating in the ocean, and we have to figure out what is the boat's velocity relative to the seagull. So we'll go ahead and let the north-south dimension be represented on the y-axis and the east-west dimension be represented on the x-axis. Let's look at a vector diagram of the situation and make the connections with our previous example. So here we have the shore, and the observer on the shore is the stationary reference frame. The boat relative to that person's frame of reference is moving with a velocity v, which we know is 9 meters per second east, so that's in the positive x direction. We have the seagull floating along with the ocean current, so the seagull is the moving reference frame, and the seagull, relative to the person standing on the shore, the seagull's velocity u is 3 meters per second north, so that's 3 meters per second in the positive y direction. And now what the problem's asking us to find is v prime, the velocity of the boat relative to the seagull. So we know from our equations on the previous slide that v prime is equal to the velocity from the stationary observer's point of view minus the velocity of the seagull relative to the stationary point of view. So we can go ahead and write that. We're going to write the velocity vector from the stationary point of view for the boat. So this is the boat's velocity vector, v. It's heading east. So that's 9 meters per second times the I unit vector plus 0 meters per second times the j unit vector, because the boat relative to the person on the shore is moving east. It has no motion north-south. We're going to subtract from that the velocity of the seagull from the observer's perspective standing on shore. And it has no east-west movement because the current is due north. But relative to the observer on the shore, the seagull is moving 3 meters per second north. And of course, we're subtracting that vector from the boat's vector. So when we go ahead and do that, we wind up with the vector v prime, the velocity from the seagull's point of view, is 9I plus negative 3j. Now, if we look at it visually, we're subtracting the u vector, so that means we have to flip its direction. So this is that visual vector addition, and it leaves us with a vector v prime. Mathematically, this is it in unit notation, and if we want to find the magnitude of that velocity vector, we use the modified Pythagorean theorem, and we find that from the seagull's perspective, the boat's moving faster, 9.5 meters per second compared to the 9 meters per second for the stationary observer on shore. Also, the direction the boat is moving is different. The seagull sees the boat moving at a directional angle of negative 18.4 degrees. That would be below 18.4 degrees below due east. In other words, it's moving a little bit southeast, whereas for the observer on the shore, the boat was moving due east. So this is how we handle and analyze problems of relative motion, where you have two frames of reference, one stationary and one moving. Well, this wraps up our podcast on two-dimensional motion. We've covered a lot of information. I hope you found this helpful. Have a good day.